Thank you for the invitation and for the kind introduction, a little bit overblown. So you have heard from the regulators, you have heard from the academic, you have heard from even the United Nations. Okay, so I am a practitioner, I'm a building consultant. I design building for a living, you know. So I'm going to give a bit of perspective on how we do it, you know, as a designer. Short synopsis, you know, what I'm going to talk about. What I'm really trying to say in this paper is, if we're going to talk about building energy, the first step is we actually must try to understand, you know, what are the components in building energy and how they actually affect. If we change, you know, a certain component, how is it going to affect? Because the reason is you can't actually control, you know, what you cannot measure. If you don't understand how much is it, you cannot control it. But if you can get a handle on it, how much it costs, you know, then maybe you can try to control it. So that is the gist of my paper. And of course, the last topic is benchmark. How do we benchmark buildings? Why do we need to benchmark building? So these are the topics I'm going to talk about. Cybergaya, I'll talk about cybergaya. What are the components in building energy? Now, a lot of the things have already been repeated in the previous two other speakers. So I'm really going to go very fast so that we can go for lunch early. But perhaps maybe there's some ideas here which are probably new to you. I don't know. Yeah. So, what are the components? And I'm actually looking at it from a theoretical point of view and from a building designer point of view. The first picture I'm showing you is actually not a Malaysian, what we call it, building energy usage. It is what we call it from a temperate climate. If you look at it, they have space cooling, they have space heating, and it's something like 25% is on heating and cooling. So, but lighting is about 25% too. So that's the first context. Second context, if you look at in fact, the Americans, you know, the American Department of Energy has one of the best database on building energy, and they have been collecting this data for the past 10 years. And this is what they get, you know. On your left, because if you look at temperate climate, they're a little bit more complex compared to tropical climate like this, because ours is 100% cooling. So how they quantify it, they say heating degree day and cooling degree day. So the one on the left is in colder climate. That means they have a lot more. No, the one on the left has a lot more heating degree day. That means on the hotter climate, and the one on the right has a lot more cooling degree day. You know, a lot more colder days. So, but you will find that they actually come up to the same. But what happened is that maybe those in the cooler climate, you know, perhaps use less energy. You know, in fact, I would think that those in the temperate climate, where the heating degree day and the cooling degree day somehow balance, you know, they probably can use less energy because they have less need for heating and they also have less need for cooling. And they will make use of what we call ambient temperature, you know, to actually cool the building. And that's where things like evaporative cooling works in that kind of condition. But it does not work in Malaysia. Okay, another context. Singapore, they have already been doing studies. If you look at this, this is a bell curve. You know? Those of you from the universities who do statistics, the bell curve is everywhere in the world. So it also the bell curve also actually shows the distribution of almost everything, you know, from how many people who are smart to how many buildings who are highly efficient, and it shows that in Singapore, this study was done something like almost 10 years ago, you know. The mean average, what we call it, the root mean square building, which average is around 220 kilowatt hour. That's in Singapore. And if in Malaysia we have 300, means we are not very good, huh? So it's like, you know, you pay for a expensive Mercedes-Benz, you know, and the Mercedes-Benz is running at 10 miles per gallon, you know. So that's terrible. So finally, this Malaysia. Now the context in this is that we try to understand what are the components in building energy. And the first thing we can see that 46%, you know, 46% is like 50 over percent is aircon, 50 to 60% is aircon, 20 to 25, 30% is lighting. And it is actually instructive to note, statistically in Singapore, even as far back as 10 years ago, aircon only constitute 40%, which means that our aircon here is pretty inefficient, you know. Two reasons. In fact, I used to do a lot of government building, you know, and we said that after you finish the government building, and if you go back there 3 years later, you wouldn't want to look at it, you know, it's so terrible, you know. At that point in time, I'm not sure now, I've a bit lapsed on government building, but my last one I did was the early 2000. It's not good, really, it's not good. So, that's the context. Now, okay, we have understood the what are the contexts, what are the energy components. The low-hanging fruit, the first one we said is aircon. Well, that's the biggest part, so let's target it. The second one is lighting. So now let's look at it from the theoretical point of view. I think you've seen this graphical representation on what constitutes the building energy. If this one is actually more intuitive, if you classify them by usage type, you know, the blue one is aircon, yellow is lighting, then you got the power point, you know, and then the rest is utilities, lifts and so on. And you can see if I look at aircon, you know, which is about 50% of building energy, you have something like 6 or 7 items there, you know? And this is actually the domain of the design engineers like me, you know. If you look at it, aircon, when I talk about heat load, there are two kinds of heat. One is called sensible heat, one is called latent heat, you know. And that's where if you go to Nyong Kong's class, you know, you get bored, you get stiff bored just looking at the psychometry chart, you know. Latent heat, sensible heat. If you do what we call it, chill beam, no latent heat, all sensible heat. But if you are designing a data center, it's all sensible heat, fantastic, you know. But other problem comes in. Okay, fine. So you must understand all this before we even try to go into design. Now, suppose let's say I want to design a certain benchmark. Let's say building energy. Then, because to actually define a standardized energy metric, I must standardize certain parameters. So, you know, what are parameters? Hang on, I'm skipping a bit. Okay, let's go back afterwards. What are standardized parameters and what are parameters within your design? And then what are parameters which is outside your design? So parameters which are outside your design are like occupancy, like maybe building usage. Is it an office? Is it a hotel? So outside your design. So if I want to define a building energy, then I would want to standardize certain things, like even hours of operation. For example, one office operates 3,000 hours a year, certain office operates at only 2,000 hours a year. So, so this actually will actually make it not comparable. So to make it comparable, I can actually use all these metrics and try to standardize it. So these are the lists. So if you are actually a student, you know, doing a theoretical study at building energy, this will be the list of parameters you will look into. And for each parameter, you can actually assign a certain formula to it. You know, for example, we are talking about these are the three major things which affect design. The first one is solar heat gain in Malaysia, a tropical country, you know, and solar heat gain principally affects your cooling load. Sun position calculator, The other one is the thermal mass. Thermal mass. Actually, there are two issues. One is the building envelope. The other one is the thermal mass. Thermal mass is how much heat they can store. For example, in old kampong house, which is made of timber, their thermal mass or the thermal heat capacity is pretty low. So in the daytime, they don't store a lot of heat. But which means at the night time it has less heat to radiate. But in a concrete building, it will absorb heat, and in the night time it will radiate heat, And you can see that, for example, you go to any campus, polytechnic or school campus where there's a lot of concrete paving, and if you go to the concrete paving at night, you can feel the heat radiating. So that is also a factor when we do heat load calculation. Human occupancy pattern. I'm going to talk about that because this is one of the major issues, and that's why when we want to actually define building energy efficiency, we actually have to define it for a certain kind of building stock or building usage. And then of course issues relating to system design, Air infiltration. Later I will show you that a lot of people don't realize, but air infiltration is actually a major issue in aircon cooling design. But air infiltration is actually not a domain of the aircon engineer. It is actually the domain of the architect. Now in temperate climate, they have this campaign, seal your building, but in a tropical climate, we don't have this kind of thing because we also need air movement, we also need fresh air. So how do you control that? And so these are some of the issues we're talking about. And chiller design, are you having a COP of a very inefficient chiller or an efficient chiller? And on top of that, even if you have efficient chiller, you must understand loading. As an electrical engineer, when we do load studies, we always talk about base loading and peak loading. Base loading is a machine which is always on all the time because the load is there all the time. Peak loading is when it caters for the swing, the temporary swing, the sharp rise. And I was quite amazed because as an electrical engineer, I was looking at aircon engineers designing 5 units of 1,000 tons chiller, and I said, how the heck are you going to cater for the peak loading? I didn't have an answer, even till today. But I understand. Finally, when we started GBI, aircon engineers are now starting to size the chiller for peak loading and base loading. So system design issue. Now the next one I'm really going to talk about is load profile. This is any consultant, designer worth his salt do capacity calculation. That's the first thing you do. But of course, they can't teach that in university because a lot of it is what we call expert knowledge. For example, how much does a building cost? Is it 100 years ago? About 10 years ago, it was like 150 ringgit per square foot. Government building, now it's like 300 ringgit. 20 years ago, or 30 years ago, government building is always cheaper than private building. Now the other way around. I don't know why. But it's a fact, and I have facts and figures to back me up because I've done government building projects and I've done private projects. So back to here, we have a lot of rule of thumbs. It's like 10 watts per meter square for lighting, and that kind of stuff, So load profiling, because when we want to actually design, we must understand. For example, I will show you this. Okay. Different kind of building. If you have a hospital, I think you're familiar with that load profile, daily load profile and a weekly load profile. Typical office, they're off Saturday, Sunday, but 50 years ago, Saturday was still working. Some office maybe Saturday half day, so that's why you still see the bump on Saturday. So if you look at hospital, it's like it runs 24 hours. Now, how do you actually calculate the heat load? For example, if you look at some of the software they use a simplified OTTV to actually generate the aircon load. But the aircon load is only generated for the daytime. Now, in the intermediate period, especially for a hospital, when the sun is down, the OTTV is different. So you have to take that into account. And hospital never sleep, but in the off-peak period, it is at pretty low load. So which means their base load is high. The base load is high. And the peak loading is not as high percentage-wise compared to the base load. So when you're designing a chiller strategy, it has actually very important implication. Very important implication. Now, if you look at a mall, the mall is, you look at that, their load actually peaks during the weekend. Not only do they have weekend loads, they also have seasonal load. If you're designing a mall, they have this thingy, December, that's the seasonal one, and in December, the load will actually, you may even be running at 110% of the chiller. So do you design your chiller for that 1 week a year? And which means most of the time you will probably be running at half load capacity, So what would be your strategy? So understanding load profile is very important. And once you understand that, this is the domain of the theoretical engineer. And to a certain extent, design engineers, even though they are supposed to be practical, they have to understand the theoretical aspect of it. And that's where we come in. Once we understand the building model, the building envelope, the usage pattern, how heat load is calculated, then we actually do this, and that's how most software actually design. First, you identify what are the parameters and boundary conditions. I'm going to explain to you what are parameters. Parameters are values affecting energy use. Boundary condition, well, it's because I'm a consultant, I use words like that so that you can pay me more. Actually, boundary condition mean wall and ceiling and stuff, So, internal boundary, and then you got external boundary. External boundary like sky condition, So these are some of the stuff. When you actually go into a detailed design, it's really complex. But as a designer, you are supposed to be expert, and we are supposed to know all this. You're supposed to know all this, and that's why we said for a good designer, we always recommend you must attend the aircon design course. We have actually 3 levels, beginners, introduction, intermediate, and advanced. Maybe they got one last one called guru, Okay, yeah. So now in the maths modeling, which is usually what most designers do too. There are two actually part to the calculation. One is they use the mathematical modeling. So for example, when we calculate aircon, we make use of what we call Carrier manual. Carrier manual actually gave us some kind of mathematical formula which gave us a very good approximation of the actual load. So the mathematical modeling, and that takes into account the sun position, the solar irradiance, and even the heat transmission, based on your building envelope. So this is what we call the mathematical modeling. Now the other part is the expert system. Expert system means actually it's an art. You can't teach that in university. So expert system means it's because I've been working in it like 10 years. I know it's roughly there. For example, cannot run away. If it's not aluminum and steel framework, it's probably 30% WWR, most probably. If it's 30% WWR, probably your OTTV, without calculating, I think your OTTV is around 60, cannot run away. So that's the meaning of expert system. Because we have been doing it so often that we have facts, data at our fingertips. And for example, when you design load, the estimate load, all load estimation are basically estimation. And when we are making estimation, they put in diversity factor. Diversity factor means, is it 0.8 or 0.7, Even the best software, even the most expensive IES software use diversity, and they're like, how many diversity? More than 10 diversity. And if you do not know, they give you default value 0.8 or 0.6 or whatever. No? But if you're an expert, somehow you know, what are the diversity, whether it's 0.6 and 0.8. Now later when we come to benchmarking, these, what we call diversity factor, for the expert, that is where you can determine whether you pass or fail. Because if you pass, you're eligible for tax exemption. If you fail, sorry lah. So we have listed out some of the issues. For example, even plug power outlet, to a certain extent, it is a function of occupancy pattern. For example, if you're designing for a stock market, there are a lot of plug points, and of course, the plug point usage will depend on the occupancy pattern. In an office, in fact, the office in an office, a lot of people think if I put 10 plug point per square meter is going to be like that. For example, in a house, even if we say, even if you put one plug point or you put 10 plug point, the average power is going to be 4 kilowatt for a middle class Malaysia. So lighting power point pattern is really more a function of the population density. If you got 10 people working, then they're going to use so much load. If you have 1 people working in that space, then it's only going to be so much load, whether you provide 100 plug point or 10 plug point. So if you under provide a plug point, then organically the user will expand your plug point somehow, like what they're doing here now. So now you understand that. Next, we said, what do we normally do? In design, we advocate passive over active. Passive means you design a building which is intrinsically low energy, which means that means to say the most sustainable building is the one which do not need to use aircon, and it's still comfortable. Don't forget IEQ, comfortable. So if you can design a building, your kampong house no aircon, and it's nice and airy and comfortable, no need aircon, right? So that's the most sustainable building. So passive over active. And passive measure, I think I'm going to skip this. I think you you are aware of this. Now, I'm going to go on to a case study because we're trying to identify, which is what most consultants do. Because once you can identify, then you say, I don't have to work so hard, I know where the low-hanging fruit. Straight away I do go for the low-hanging fruit, and then I don't have to waste my time studying whether the plug point needs 3 circuit or 4 circuit, that kind of stuff. Okay, I have 4 scenarios. Why I'm doing this? Because I want to show the effect of roof. You have the first case, single-story building, area of roof over the square feet is 100%. Roof 2-story, 5-story, and 10-story, and that ratio is the area of the roof over the total built-out area. And these are some of the basic parameters I've done. Base study, which is normal. You can see most building, their WWR will be around 30%, roughly there. Unless it's one of those new aluminium and glass, then it may be 90% or 80%, like the new JKR building is, I think, 80% glazing. And if I do a normal design, there's normal braid, you can see OTTV 68. So, which means there's another expert system. Now you know, any building which is 30% glass, probably going to have OTTV somewhere in the region of 60, So, first study. Occupancy rate, because I think we have this argument, I think what ST building has 32 meters square per person, and my office got 12 meters square per person. I'm sure those of you who works in PJ, how many 10 of you are crammed into one floor in a typical shop lot, right? So that's about 10 meters square per person, you know. Does it affect your BI? Why? Because we call this, what we call this, a critical test. There's a term for this, you know. Non-critical test and a critical test. A critical test is when it is a life and death. If you pass, you are eligible for something. If you fail, sorry, you know. Non-critical means you pass, fail, doesn't matter. You know? So very critical, you know. And you can see, you know, I have base case and design case. And in the case where actually the roof and floor ratio is around 20 to 50%, you know, it actually is your borderline, you know? Borderline, scoring 2 points additional. So great, your project. But a lot of argument over this. You know? So, but we say never mind, we give you the benefit of the doubt because currently BI does not, actually not only Malaysia, even in Singapore, even in America, the building intensity do not take into account building occupancy rate. But however, I think the UNEP common carbon matrix is now attempting to include, instead of kilowatt hour per meter square per person, it is kilowatt hour per occupant per year. Of course, we are going to argue. I know a lot of people are going to argue, you're right, I'm wrong, you know. So, but we stick to kilowatt hour. But what I'm trying to illustrate is, you know, STBD is a bit unfair. You know? Maybe you should ask them to close down half the floor and guarantee you 40% energy saving. Guarantee, you know. Yeah. So first one. No, it's like the recently we had this township tool and then a high class development because the more dense your development, the lower your carbon footprint. And they got this developer who is developing for the upmarket, you know, and he's like 1 DU, 5 acre per DU. DU means dwelling unit. Wow, that's not very green, you know. So, okay, same implication. If we zoom on, you know, the enhanced case, when we are borderline between losing 2 points, really, you know, if we actually consider occupancy. But of course, if you are talking about between 10, you have to actually from 10 to 30, then you see the effect. So that is actually the implication. The next one is let's look at the various issues which actually affect your aircon. And you can see base case, improved case, and so on. 100% roof, 10% roof. And notice, you know, infiltration air. A lot of people don't realize it actually constitutes something like 30%, you know, the air infiltration in the base case, whereas in the enhanced case, like that means like 20 to 30%, you know, of your aircon load is due to the air infiltration. And I remember when we were talking about shopping mall, you know, and if shopping mall has something like 30% F&B. F&B means food and beverage, and F&B outlet have a lot of cooking places. And when you have cooking places, you have the exhaust air, and from the exhaust air you get a lot of air infiltration, and it is really going to load up your aircon. And so what we do actually is we look at the exhaust air as a problem and try to solve that problem. You know, so I think some of the issues, some of the solution people are offering are spot exhaust. You know, they actually even control the exhaust air coming into the kitchen. So see, 30% to 40%. You know. So how leaky is your building? You know, and it also got to do with how the architect design his building. How the windows are being fixed. So make sure the windows are sealed. Otherwise, yes, you're actually throwing money out. And you can see that the people, okay, if you look at OTTV, it's pretty constant, whether it's 100% roof or 10% roof, and you can seriously say that the building facade constitutes something like 15% of aircon energy, and aircon is like 50% of total building energy. So which means it's like 50% of 50% of your whole building energy. And now if you look at equipment, that's pretty huge. Equipment has two implications. I'm talking about electrical equipment. They contribute energy directly by using electricity. And next is, because of the heat given out, they also actually load the aircon. So electrical equipment like your motors and so on actually contribute to your aircon load 2 times. So if you actually use energy efficient equipment like HEM, high efficiency motor, you can actually save energy 2 times. So by analyzing all this, we straight away can zoom in. Straight away once we know all this, we say we know already standard office building. I'm going to target this. I'm going to target that. So that's the purpose of this exercise. Now roof. Goes without saying, you can see, roof, if you have a very large roof area, normal, if you're doing, let's say, a factory design, 2-story, large roof, you're going to have this, and you have to concentrate on your roof insulation. And you can see, roof at 100%, base case, there's as much as 14%, 15%, contributing to your energy, your aircon energy, And whereas for building envelope is pretty constant, whether the roof is 100% or 10%. So there is maybe some kind of idea you can get from there on what you should target first. So conclusion, leaky building, which a lot of people don't pay attention to, and a lot of public buildings are very leaky, and that's where they waste a lot of energy. Facade, it's about 15%. So which means if I'm going to spend, it's like if I want to spend 1 million ringgit on my expensive brick, you go and calculate. That means without those expensive software, straight away, you ask the client how much your electricity bill. If the guy says 100K month, straight away you can find out how much the facade is responsible for that 100K a month. 15% of the 50% is the facade. If I'm going to spend 1 million on a facade, what will be my payback? You can do it on a paper envelope and do it, So expert system, So you don't need expensive software, and you're there, Now once you know all this, what I'm trying to do is, I think you have seen some of it, is Steve has done the same thing, but I have listed some of the 13 issues that most designer will do. These are the easy one. Unless you got a designer who's so entry level, then sorry. This one you do. I've listed out the 13, and this one you get. And notice, actually I start with 168 kilowatt hour, not 200, because 200 is a terrible design, actually, it's a very bad design. And if you go there step by step, step 1 to step 13, and what are the steps? All listed here. For example, the first one, easy one, I just improve OTTV to 50, and despite what a lot of people think, to improve OTTV to 50 doesn't mean you have to buy Looi glass, because they are terribly expensive. One method is just to use tinted glass, or you say glass with a low SC. It's just tempered glass, but glass with a lower SC. Instead of solar shading of 0.8, it is solar shading of 0.4 and 0.5. And usually that means tinted glass. And just by using tinted glass, you can actually improve it to 50, and you can see that your energy, and I can tell you this chart is pretty clear. It's a very good guide, whether you're doing any kind of office building, 10-story or anywhere from 5 to 10-story, you'll get this figure. Or if I'm going to get a 50, from a 68 to 50 OTTV, my BIT is going to come down from 163 to 159 or something like that. Cannot run with. Roughly there. So you get that kind of idea. And you can see between 5 and 6, that seems to be a major jump. And what is that? 5 and 6. 5 is actually daylight. So apparently daylight is actually a very useful way to do it. And if you know how to do it, it can be done quite cheaply. It can be done quite cheaply. So just by utilizing daylight, you get quite a massive jump, 140 to 132 or something like that. So the whole idea of this exercise is to either no more time, right? Okay, thanks. Anyway, the whole idea of this is actually to identify, because consultant like me no time, no time to go and study, so we straight away we know what are the best strategy and we zoom on and finish the job and get our fee. And if you look at it, 9 and 10, another major jump, And what is that 9 and 10? And 9 and 10 is, wow, that works if you are talking about a 10-story building. I'm going to improve my water side. That means putting VSD pumping, maybe sizing of the piping and so on, And because one of the major issue in pumping system is slipshot design. First when the designer design, he says, okay, I need a 10-meter head, and then when he choose the pump, it's always like, okay, I'm going to choose a 10 horse. And when it goes back to the supplier, you probably get a 12 horse. It's like 50% oversized. So simple things like that, and you get a big jump. Now, if we go back to the cost, you see, BI reduced from 164 to 98. And we say if you are any consultant who do a design, more than 200 is a terrible designer. Reduction in energy approximately 40%, and we actually tabulate all this cost, about 3 million. It's about 3 million. And you get an energy saving of 1 million a year. So ROI 3 years. So we said it's silly not to be doing this. It's silly not to be doing this. Okay? So and energy cost is going to go up. If you look at your bill, they said just charge additional 1%. I just saw my bill, 1%. So 3 years. Now this is interesting because we go back to this chart again. How much aircon comprise of the whole thing? And when I'm talking about the BI 168, we said we are fairly competent design, And aircon is 41%, So my conclusion is, if your aircon is more than 50% of your building energy, your design is no good. Now, this is the baseline case. If you look at the enhanced case, the aircon came down to 33%. What came up is the other load, the miscellaneous load, 35%. Because miscellaneous loads are all the other motors, and you can't change them, beyond using high efficiency or Energy Star rated equipment. And you can see, from the equipment miscellaneous load went up, the blue one, miscellaneous load, 24% went up to 34% because the aircon shrunk. So another conclusion I can make is, aircon in Malaysia, any aircon building, office building that is, if the aircon constitute more than 50% of the load, is a terrible design, it's a terrible building. So perhaps maybe even universities can do very basic study like this, not rocket science. And just from this kind of study, you can find out a lot of expert systems which can actually help designers. So I think that comes to an end, but I'm going to go on to a quick one. Why do we need to do benchmark? Because some of the major issue is, I think Steve's talking about carbon, not carbon. Currently, there are a lot of what we call that performance-based contract. And in the performance-based contract, they actually, the banks only pay you when you achieve a certain targeted performance. Now the problem is, the bankers, they're not engineers, They have a hard time understanding whether you have achieved or not. So defining the building energy intensity is very important because it's going to go into the contract. And I can remember as far back as about 5 years ago, there was one contract, there were huge argument. The ESCO actually did something, it was funded by the bank, did something, and after finish, he tried to claim, and the client argued that the energy saving was not due to his work, but due to his staff being diligent. So defining standardized BI is actually very important for us later, especially if you want to go into energy performance contract. But having said that, you need to have standardized terms like 2,700 hours. However, let's say in a hospital case where it's running 24 hours, or in a hotel case where it is running 24 hours, but not like a hospital, because in a hotel case, the peak load will come in depending on the hotel, probably in the evening, in the evening when most of the guests are out. So standardized testing, high-stake test and low-stake test. High-stake test means it is very crucial. If you fail means for example, if you fail the exam, you don't get your degree means your career is going to be affected. So high-stake test and low-stake test. So we said that currently the BI under the GBI tool is a high-stake test because passing and failing. That's why all designers they monthly also must pick the figure become 150. Otherwise you don't comply. And if you don't comply, no tax eligibility. That one is serious, very serious consequences. So we call this a high-stake test. Now, when we're talking about how we define a benchmark, there are two ways of doing it. One, we call it norm-based. Norm-based means we select, for example, shall I set, for golfers, let's say, shall I set a passing mark? This group, I find out what's the average handicap. If the average handicap is, let's say, 16, then I set the passing mark at 16. We call this a norm-based test. Now, this is good because in such kind of test, if the standard move, then your benchmark moves with the standard. That's called a norm-based test. The other one is called a criterion-based. Criterion-based means I set a value. I don't care what is the average here. I set passing mark is 14 handicap. So if you don't achieve 14 handicap, then you fail. So in GBI, where we set actually 150 as the entry, there is actually a criterion-based test. Now the problem with criterion-based test is that it is rigid, it's fixed. And to be able to set an absolute value, you must have enough data. Enough data. You can see, the first line there is actually, that is the value you fix, that's the standard you fix. And then the top line is advanced level, the bottom is fail. Whereas in the norm-based is that you move with the bell curve. The passing mark is what the average mark of the average person in the group. So there are two ways. So that's how actually other tools do it. One of the ways is instead of setting an absolute value, I think that's how the American ER do it. They collect a lot of data and then they benchmark your energy performance based on the same building stock. And if you falls within the mean of that building stock, then you pass the test. And it will also tells you how far you're above that mean, and it will tell you that whether you're a 5-star or a 4-star. So that's one way of doing it. So now GBI is what we call a criterion based. You set absolute value. And you can see because of building usage, data center we have something called PUE. Why PUE? For example, I'm doing one data center. The building load is only 600 kilowatt. but the data load is 3 megawatt, and it's all sensible heat, no latent heat. So, so obviously we cannot use kilowatt hour per meter square. We have to actually use another metric. We call it the PUE. And currently in GBI we're grappling with another metric for airport. Can we use kilowatt hour per meter square? We find that we cannot, maybe not, maybe we have to use kilowatt hour per passenger landing, maybe, So that shows you that, and you can see entry level office building, 150 we said, and item 2, I can give you some very good example because we did some pilot study with the Shopping Complex Association in one of the complexes in Bangsa, and we found that the average shopping mall uses something like 400 kilowatt hour per meter square. And after we did something, we managed to bring it down to 300, 240. And that's the entry level. And maybe even 240 may be a bit difficult to achieve for shopping mall. And this is the standard set in GBI. I'll go through it quick. And the last one is status of GBI. Within 3 years, we have achieved 26 million square feet of certified. So, which means we are actually creating market for green pass, last time when they started the KCAT, all illegal copy. When they licensed it, we were so used to it, we no choice, we have to buy the legal one. So we create market. Number of tools, 10 tools. 1 year ago, 192 projects registered. 1 year later, 290. I understand July is 311, the figure, 311. And we have, within less than 3 years, 2.5 million square meter worth of certified building. And this only represents something like 25% of the registered project. We foresee within the next 6 to 1 month, something like 6 million square meter of project is going to be certified. So we think there is a big market for green building. I think with that, this is a green township tool we have launched in December, and currently we have 9 townships, 7,500 acres of property development. From Sunway is one of them. They are getting certified now. And interesting thing about Sunway is that to get certified, they actually have to convert one of the existing shopping mall to be a certified building, and they are currently doing that. So they are now undergoing PA assessment. This is in Bentong, I believe. Bentong, the high class one now. Yeah. Okay, this is fantastic. In fact, for this one, because they are located in a lot of biomass, they may actually be going to install some kind of biomass generator there. So with that, I end my presentation.